Okay, so this is the second part to the first project for high-speed aerodynamics, talking about CD nozzles. So the first part was about a shock in the diffuser of the nozzle. The second part is going to be no shock in the diffuser of the nozzle. We're going to have to push the shock outside of the nozzle. So what I did was I already had my geometry. I had made that in Fusion 360. It's right here. And then I imported that in. I created my mesh right here. Like I said, I made a fine triangular mesh. It's not perfect. You can see there's a bunch of imperfections, but it gets the job done. If you want to see the drop down menu, it's triangles. And I had inflation. It didn't do much. So I just took it out. So I create a new block of Fluent, and when you create a new block, you can drag it out and you can copy the same mesh, so you don't have to do it twice. So that's what I did, because the only thing I was changing was the solution. I wanted to be able to keep both because I knew I was doing the video. So I decided to just come out, link it like this, and when you link it, you will see geometry is loaded up. Mesh. I just have to update the project, and it will go over, but not going to worry about that. So we're going to go in and view the solution now. So this one here, you can see it, the mesh is loaded up. Let's go back. We're density based, just like the other one, because we're doing compressible flow, no longer incompressible. So model. I did a different model for this one because I wanted to see how it worked. So the other for the shock in the diffuser, I did Inviscid. For this one, I did K epsilon because I want to see how the shock formed. I was curious, and I kept everything else the same. I didn't do anything too fancy with the model. So everything else is the same. Fluid, you want to go to air. You want to make sure your density is ideal gas, so we're good there. Boundary condition, same deal. The pressure inlet, because we're treating this like a reservoir that's full of like really compressed air. I set it was 1E9 pascals for my total pressure, and then for my initial gauge pressure, the static pressure, I used that MATLAB script here, and I calculated what the pressure ratio should be. So and this one for the outlet, I set the gauge pressure to low because we want that shock to go out. So I didn't mess around with that one too much. I basically just plugged in what I should have from the MATLAB script that I calculated. So same thing as before. Methods kept everything the same. The only difference is this one now has a turbulent kinetic energy, the turbulent dissipation rate, which I kept those the same. I did not bother to mess with that. So same thing here. Change the residuals down to the 1E-9. Did my initialization, and I also did the solution animation again. And I like this one better than the other one. I think this one's pretty cool. I did 200 iterations, excuse me, for my parameters. I just did a 2 interval reporting because I kept seeing it pop up on the console and figured a reporting interval of 2 is fine for this. So let me show you that playback. Actually, I have it up right here. There we go. So you can see here, you can see the shock form in the nozzle, and you can see it push out. You can see it's not as clean of a cut, and I think that's because of the model. For the Inviscid, it was nice, clean, but this one has some turbulence in it, so that's why it looks like it gets kind of fuzzy. It's not going to let me zoom in, of course. But it's not a clean straight line once it gets towards the end of the nozzle. It pushes out, and we go over to my contour on my residuals, and you can see it does some weird thing in the beginning. And then my residual starts converging and it drops down suddenly once that shock pushes out. So you have to end it. If you don't end it, then it's gonna like just completely crap out on you. I don't know why. I don't know what happens, but like I guess it keeps calculating the same thing and it doesn't like it. So anyway, I stopped this one at 1728 iterations, 1728 iterations. I don't think it ever converges. I don't know. I made it up to 200 before, or 2000, and it still had not converged. So I'm not sure. Anyway, here is the contour of our mock number. Looks pretty good. Looks like you can see some diamonds in here. So yeah, pretty neat. I don't know. Pretty cool. I didn't calculate it. I already did the report and I had to rerun this. I forgot to save it for the video. So I don't have all the contours here ready. So here's the velocity. You can see it's slow. Here in the reservoir, speeds up, get to the throat, and boom, super fast. So pressure, we're going behind the shock after the shock's already been, so our pressure is lowering, our static pressure. It lines up to everything like that we've learned in class. Same thing with the temperature. It looks, that diamond is pretty pronounced here. What else do we have to do? Speed of sound. Yeah, higher speed of sound in the reservoir, much lower behind the shock. Excuse me. So that is running the CD nozzle with the shock pushed out in Fluent.